Welcome. My name is Jakob Wagner, and together with my partner Dominga Garufi, I have the pleasure to present our contribution to the IASS conference with the title Three-Dimensional Fiber Placement in Wood for Connections and Reinforcement in Timber Structures. With this, we introduce an integrative design and fabrication method for controlled anisotropy and fibrous continuity in segmented and modular timber structures. Our work is based on an inductive research approach. We first test an idea with 3 typological case studies to then work towards a general framework of fiber placement in wood. The adaptive growth of wood makes trees some of the most performative fibrous structures on Earth. But as sawing processes cannot deal properly with complex fiber arrangements, adaptive growth mechanisms are most commonly known as a class of wood defects. The result of the development of efficient sawing industries is that wood products became reliably robust, but at the same time, the fibrous integrity of the tree is lost in the processing steps. For now, it seems that we just accepted this fact and are continuing to use mechanical fasteners as go-to connection technique. An arguably much more appropriate way can be found in one of the oldest wood joining techniques used by the ancient Greeks and Romans. The fibrous material of wood is joined together by intricate placement of secondary fibers into pre-made grooves. Only with the advancement of energy-intensive steel processing was this performative joining technique replaced by mass-produced mechanical fasteners for the construction of lightweight hulls of ships. Our hypothesis is that through digital design and robotic fabrication, we can today reintroduce high-resolution controlled fibrous anisotropy into wood. For this process, the wood is first milled to machine highly accurate grooves that serve as the lost formwork for the fibers. In these grooves, fiber bundles can be easily placed, following the precisely milled pattern of grooves. But not only can we place fibers into grooves, we can also thread them through holes. This makes possible a fully three-dimensional secondary fiber arrangement within the wooden base structure. In our first case study, we show that it is possible to thread a knot of 4 fiber loops within a solid block of material. For illustration purpose, we use plexiglass in this example. Grooves are milled into both sides of sectional plates. As they are milled from both sides, it allows a full control of the internal channel's geometry. When the plates are aligned, it is possible to pull a fiber through the channel. After the last plate is closing everything off, we are left with a solid material that is internally reinforced with three-dimensionally placed fibers. Similarly, we can use robotic milling to machine and drill into a plate from 2 sides. This allows to place fibers through the board and simplifies the manufacturing complexity. As a second case study, we show how such fabrication method allows for highly performative timber plate joints. As the fiber can be shaped into any geometry, such joints can react to many different boundary conditions, such as plate angles, force directions, and moment directions, just to name a few. We developed a computational algorithm that takes the plate geometry and the simulated forces into the segmented shell as an input and generates an intricate arrangement of fibrous joints. The fibers are then placed inside the wood, forming bending moment resistant fibrous joints. We then use electrical current to cure the fibers directly. With this technique, we were able to design and build a segmented timber shell structure which integrates architectural features as, for example, stairs, while still delivering high-performance structural capabilities. In a third case study, we demonstrate how the fabrication complexity can be simplified even further to build an irregular timber shell. Using only 4-axis desktop milling machine, custom grooves are milled into a maple hardwood dowel with different milling tools. The prefabricated pieces are then cleaned and assembled. The CFRPs are manually placed into the grooves, which are then post-tensioned with small wooden dowels for the entire curing process. A voltage of 2.8 amperes is then applied to both ends of the roving, and the resin cures, allowing the fiber to get to its maximum strength. The CFRP connection becomes stiffer than steel and forms a moment-resistant joint. The CFRP and the wood can later be separated as the materials are not glued together. Together with our workshop participants at the Smart Geometry 2018 conference in Toronto, we built a 2.5 meter high demonstrator structure using the presented fabrication technique. With this work, we want to demonstrate the possibilities that arise for advanced timber construction by leveraging computational design and digital fabrication. We are full of joy that many of our students and colleagues are currently continuing this line of research, focusing, for example, on how distributed robotics or 3D printing can be used to automate the fiber placement process. We hope that also the engineering and robust simulation of such intricate structures will be possible in the near future using advanced simulation frameworks. With this, we close our presentation. We want to thank Professor Jan Knippers and Simon Bechert for their valuable advice. Thanks also to our workshop participants, colleagues, and the organizers of the Smart Geometry Conference 2018.